Hello everyone, and welcome to part 3 of homework 4, where we're talking about implementing flash calculation functions to calculate the vapor and liquid compositions of the streams leaving a flash drum, given a specific feed. Okay, so this is it's a build-up of the previous two parts. So we're actually going to use the NRTL coefficient model in part 1, and we're going to use the bubble and dew temperatures calculations in part 2. So let's get started. So brief explanation about what a flash calculation is. So here is a diagram of what a flash drum itself looks like. So what happens is we have the feed coming in, and the feed enters a flash drum. Some of it vaporizes into a gas. Some of it remains as a liquid. And those the feeds of both sides, going up and down, are necessarily going to be different because of what we talked about in the previous part about the different compositions of dew and bubble temperatures. And if you remember that graph that shows the dew and bubble point, in this model, our feed is going to be coming in right in the center between the dew and bubble temperatures. And I'll show you what I mean by that later. But because it's coming in at both, what will happen is when the feed enters the drum, it'll split. Some will be vapor, some will be liquid. Okay, and those vapor liquid will actually follow the Raoult's law, as we talked about in the last two parts. Okay, and that Raoult's law, that correlation between pressure, or between gas phase pressure and liquid composition, that's going to be the key to solving this problem. Okay, so let's jump into it. So let me run these. So this is the same workbook that we've been working on, and we have our coefficient models and our bubble point and dew point. Let me run these cells. I'll keep them hidden just so that they're out of our way, but let me run them so that we can use them later. Okay, now while we're doing that, let me steal these lines of code because we're going to need them. Okay, so what are our initial compositions? We need a feed comprising of 10 moles each of methanol, ethanol, and water at a temperature halfway between dew and bubble temperatures. Okay. So let's do NF equals, let's make this an array. Let's give it 10, 10, 10. Okay, so there's our moles of feed coming in. So we have 10 moles in each. Then we need, let's change this to flash P so we can discriminate it going forwards. Then the next thing we need was 10 moles each. Temperature midway between dew and bubble temperatures. Okay. So what we're going to want to do is actually I want to open this. And we're going to call, let's make this a new cell. We're going to call our, so we still have our X. And we're going to call our bubble T. Given our flash P and X. Okay, so that should give us 347. Okay. So we just want the first number, so let's do the index 0. Let's call it lowercase bubble t. Okay, and we'll do the same for dew t. So dew t equals dew ideal T at flash P and X. Okay. Turn those. And then to get our flash temperature, which is halfway between, we're just going to do np dot mean of our variable bubble T and do T. Doesn't need to be an index. Let's try putting it in an array. Sometimes it likes that. Sometimes it likes that a little better. $352. Okay. So at this temperature and pressure, I believe our bubble temperature is at like 347 and our dew temperature is at like 358. So 350, 352, 353, that's perfect. That's what we need. Okay, so now that we have our flash pressure, our flash temperature, our feed coming in, let's get started. Okay, so the first thing we want to do is we want to talk about our vapor-liquid equilibrium. So let's just call that vapor-liquid. Let's just define that. It's VLE, and we'll give it a parameter in a second. Okay, so what we want to do first is we want to first look at our vapor fraction. So let's calculate NV. So NV equals, well, let's show something. So SciPy has a handy little function called xbit. It's right here, which stands for logistics sigmoid function. And it's what it actually equals is 1 over 1 plus e to the power of negative x. And it's the inverse of this function. And what this does, or what it's designed to do, is transform a function so that its bounds remain between 0 and 1. So no matter what value of x you give this function, its answer will be between 0 and 1. Okay? And the reason why that's useful is because when you're finding a root or anything like that, the only answers you can possibly get are a number between 0 and 1, aka a number we can actually use in our as a molar fraction. So we're going to use this here for I think it's pi. We'll find out when we. And we want to multiply this, or we want to find the vapor fraction. So vapor fraction is going to have to be one of our parameters. And then we're going to multiply this by our NF array. NF, big F. And what this will do is it'll calculate our molar fractions, and we'll multiply it by our total moles to get our moles as a gas. Okay. And once we have our moles as a gas, then getting the moles of a liquid is basic material balance, which is just feed minus vapor is liquid. Okay? So now that we have those two, let's look at calculating our x. So our x is our molar fraction in a liquid. And finding the molar fraction in a liquid, we take, how do I do this? Let's do y first. Y is easier. So y is the molar fraction in a gas. That's just NV divided by it's NV divided by NF. We don't want to use V here because remember V is the variable for this x bit transformation, and so it won't be what we want. So this will actually just give us this x bit output. Actually, now that I'm looking at this, I think we actually want to do is instead of using NF, let's use. So remember, NV is the moles is going to be a 3-element array with each one showing the moles of one of the components. The moles of one of the components. So actually, what we want is we want to use this NV sum NV. So what that'll do is that'll sum up all the moles in vapor and divide each component by the sum of them. And we'll do x the same way. So x will be NL divided by MP dot sum of NL. And this equation up here still works because there's 10 moles of each component, so they have to be distributed between the vapor and the liquid. Okay? Once we have that, what I think we want to do with this function that just looks at our vapor-liquid equilibrium, is we're eventually going to use it as a nested. Actually, let me do that now before I forget. So we're actually going to use this as a nested function. So we're going to define this as just flash calc. Give parameters later. And let's just tab everything over. So we want to nest this. And we're going to go back to our old familiar Raoult's law. Go back to this equation. Actually, we don't want this one. We want, let's have one with y in it. Yeah, we want this one. So we're ignoring this term here, because that's about mixing, and we're assuming this is perfectly mixed. So it's y times total pressure equal, it's the y times total pressure equals x times our activity coefficient times our vapor pressure equal, or our saturation vapor pressure at equilibrium. It's a mouthful. So what we want to do with this function is we actually want to use this Raoult's law and zero this function out. So let me show you what I mean. So one side of it is x times the activity coefficient times p star. So let's do x times the activity coefficient is our nRTL function that we made in part 1. And that one we need an x and a t. Then we're going to multiply it by, what did we say? P star. So that's P dot P vap. And if you'll remember from our previous video, that P vap will pull the vapor pressure equilibrium data at a specific temperature for each of the components. And it knows, because of that P dot and these props that we set before, it knows which component is which and can pull, the water data for the water component, which is enormously useful. Okay, so that's one side of Raoult's law. And because we want to zero this function out, what we're going to do is we're actually going to move this side over too. And then we're going to later on ask a root finder function to find the zero of this function. So this expression then becomes true. So we're going to do minus y times our total pressure. Okay, so right off the bat, you can see that we're going to need our, well, let's get to that in a sec. So, all right, so we're here. So you can tell that we're going to need an x, we're going to need a t, and we're going to need a p, in addition to needing a nf. Okay, so since we can get x from nf, let's just do nf, and we need a temperature, and we need a pressure. Okay, so let's x equals, that shouldn't be an x, that should be a z, because z is what you normally use for the feed. Yeah, mp dot sum nf. Okay, so can't remember if we'll need that, but it's always good to have it. Okay, so now that we have this function here, we're going to use the root finder and use a root finder to calculate for NF. No, we don't want NF, we want MV. And that equals NF times our x bit function. And what we're going to do here is we're actually going to find the root of this. So let's use the root function. And as a reminder, root finds the vector function, and it needs a function. So our function is VLE. It needs an initial guess, which we're going to give it at let's go to z and see if that works. And then we'll see if that's all we need. And let's just return NB. That's not our final answer. I just want to make sure our root finder function is working. So let's do flash calc NF flash T and flash P. That should be capitalized. Here's just x bit as it is. So it's not from NumPy. It's good to know. So it's not happy with this guy. So let's throw a dot x on here, see if that works. Okay, so that way it worked. Not happy with that though. So I'm going to return NV not NF. Interesting. So these are tiny numbers, which means the program is trying to tell us that pretty much all of it's going into vapor. That makes sense though, because if we're picking a value halfway between, we'd expect at least some liquid. Okay, so let's finish coding this out first, and then we'll deep dive into a couple things. So let's finish this out by calculating n sub L, which equals nf minus nv. Then we have y is equal to nv divided by. So we're basically just kind of copying over the equations we had up top to get our x's and y's. That's sum of n sub L. Okay, so and what we want to return is, what are we asking for? It's asking for vapor and liquid compositions. So let's give them that. So it wants x, it wants y. And let's also give it a molar fraction so that we can actually see what we're looking at. So let's do NV, so NP dot sum NV divided by NP dot sum of NF. So that'll tell us how much of this is actually in the vapor phase. Okay, we'll run this. Let me comment out this print. All right, so we're still getting, so this is basically telling us that it's all in the vapor phase, pretty much. And yeah, so what does that mean? So our flash temperature that we're working with is at about 353. And our model up here predicted our due temp at ideal like with the ideal at about 358 or so. Okay. So what might be happening is it's probably all working actually. And the true, because remember we used ideal assumptions, the true dew point might actually be around 350, 351, 352. Because if it is at about 352, then this answer makes sense. That it's all going to be vapor. So how do we go about, using the real method? Well, I have here our professor's code, where he did something similar, except he actually used the full, did not do the ideal situation, he did the real situation. So let's actually copy that over, and let's give that its own, put it here. Then we'll have to change it because his are a bit different than mine. So let's change this to, what do we call them? NRTL Einstein. NRTL Einstein of X and T. We call this do ideal P. Same changes here. NRTL Einstein. Alright, so let's run that. Let's see if that worked. So let's run do T underscore NRTL X and RP. Let's do flash P. I'm not sure what exactly is wrong, so let's just use the other model we have, the matrix vector. Is there an Einstein in here I'm missing? Yeah, we don't use an Einstein here, so I'm not sure what the error is. Flash P, we got X. Why is it telling me it's not defined? So it's giving us 351.8, whereas our old calculation would give us 358. So you can see there's a big difference. So I'm not sure what it's saying here, but it is running and it is working. So let's just get rid of this for now. And it is working because that is what it should be. And you can see by assuming the ideal and not implementing an RTL method, you can see that big difference. It was almost like a 7-degree difference, and that really threw off the rest of our calculations. So we're going to use this. We're going to use this flash T, which is now at 349, and that should be safely within our range. As we run this here, you can see, hey, now that we have, first we have the compositions of the liquid, which is mostly water, as we'd expect, with a lot of methanol and ethanol still. Then in the vapor phase, we have a lot of methanol, a lot of ethanol, and still a good chunk of water, about a quarter. And about 64% of it winds up in the vapor phase. So as you can see, by splitting it, by doing this flash drum, we were able to achieve these conditions and make the split happen. So I think that's everything we need. So there we go. That's how you do a flash calculation. And we learned today that using that ideal dew point is important. So that's it for homework 4. So thank you all for sticking with me and watching this through completion.